but every component itself has different potential for issues with reliability, especially if the PCB goes into a harsh environment. For example, like being mounted outdoors on some kind of communications pole or underneath the hood of a car, or even worse, like out on the ocean somewhere or going up into the atmosphere or into space. And so those types of environments are extremely challenging for electronic assemblies.
Hello, everyone, and welcome to the Altium On Track podcast. I'm your host, Zach Peterson. Today, we're talking with Tony Lentz, chemist and field applications engineer with FCT Solder. I think this is going to be a fun discussion today because we'll be talking about some issues with assembly, and I think this is easy for designers to overlook some of these issues at times. So I'm very happy to have Tony on the show. Tony, thanks for joining us.
Oh, thank you for inviting me. I appreciate the opportunity.
Absolutely. I've said many times in the recent past on the show that I have made it my mission over 2022 and now going into 2023 to learn as much about the manufacturing process as possible. And that includes assembly. And I think that also means you need to know a little something about solder beyond just kind of the basic thermodynamics and composition. So maybe if you could tell us how you got into the industry and how you got to be in your current position with FCT.
Okay, certainly. Yeah, I graduated from school with degrees in chemistry, and I wanted to put them to work. But at the time, like a friend of mine knew a professor that I was currently taking a class from, and he offered a job opportunity to me in the printed circuit board manufacturing industry. And so I went to work as a process engineer in a bare board manufacturing company, which uses a lot of chemical products in order to produce bare boards. And I got to put some of my degrees to work, but really it wasn't what I was looking to do. I always wanted to do R&D. And so about 5 years later, I got an opportunity to come to work for FCT companies as an R&D chemist and also a laboratory manager. I did quality control analysis, and I also did some customer support. And over the years, that company has split off into several sister companies, and one of which is FCT Solder. And I got an opportunity to work specifically for FCT Solder, supporting the electronic soldering products that are used for printed circuit board assembly. And that's been an interesting 10 years that I've been doing that now. And yeah, it's been fun. It's been exciting. I've learned a lot over that period of time, for sure.
So I take it the company manufactures and distributes solder formulations?
Yes. Yeah. We're a group of chemists that formulate fluxes, solder pastes, wire solder fluxes, liquid fluxes, those sorts of things. And our sister companies still are in business, and they're still formulating all manner of products to do printed circuit board manufacturing and assembly.
I think when some designers who maybe aren't closely involved with a high volume manufacturing process have to plan for assembly, they're probably relying a lot on their assembler to make the right decisions about solder. I mean, maybe they're choosing, lead-free versus leaded, but aside from that, if they're not prototyping at home, they're just kind of relying on the assembler to make the right decision. Would you say that's a fair point?
It is a fair point. Yeah, most of our customers are contract manufacturers, and they're being handed either printed circuit boards and components and saying, hey, solder this together, make it work properly, or they're being told specifically what materials to use, including the solder products, but that's more rare. Most of our customers generally have some control over what they use, and they'll spec in a series of solder pastes and fluxes, and then they generally want, if they work fine, they don't want to change very frequently, which is understandable.
Well, one thing I'm wondering is how many of your customers are coming to you with a set of performance requirements? Because I think if you're a designer, you're operating under a set of standards, it's easier to specify performance requirements that the solder has to hit. And then it's up to the assembler to figure out how to get to that point.
Yeah, usually our customers are going by the IPC J standard documents. So they're looking at J standard 001 and IP 610A. As the main documents that guide the quality and the assembly of printed circuit boards. But then they're also looking to J standard 004 for fluxes, J standard 005 for solder pastes, 006 covers solder alloys. And so they're, generally speaking, they just want to specify products that fit those standards, which all of them pretty much do. But then on top of that, it's a combination of if their customers do require something specific, obviously they will buy that certain solder paste or flux, and that's what they're going to use. And they'll probably use that on other products as well, just because it's easier to not have 5 different solder paste in house and only standardize on maybe 1 or 2. That's generally what we run into.
And then what about low temperature requirements? I know that low temperature solder is desired in some cases. Do you have customers coming to you for that and requesting low temperature solder alloys?
We do. Yes. Low temperature solder alloys have been around for a couple of decades. Originally, it was a tin bismuth eutectic alloy that was used that melts at about 138 C. So it melts quite a bit lower than even tin lead solder. And there's a problem with that alloy, though. It generally is very brittle. And so they don't do well in any kind of environment that has vibration or drop shock or severe thermal cycling. Those solder joints tend to crack. And so over the last, I would say 5 to 10 years, there's been a lot of effort to develop higher reliability versions of those low temp alloys. And now that's what I see at the technical conferences that I go to. There's a lot of papers being presented on low temp alloys that have additives to modify those reliability properties.
Well, what kind of, or I guess, what does the research landscape look like for these types of materials? Because I think this is certainly my perception, not being an assembly expert, but it's essentially just a blend of metals. How much research can you do on it to try and improve the reliability? And I think it's natural to kind of wonder how much effort is put into this from the R&D side to try and get better and more reliable stuff that you can actually work with at low temperature.
Yeah, I think the trick there is, well, on one hand, you're really right. That's a blend of different metal alloys, and every additive adds different structural properties, different intermetallics to that solder joint composition. But really, you've also got the added metals of the PCB pad itself and then the component. And when you solder those together, some of those metals dissolve into the solder joint, and that can influence the reliability of the overall solder joint. But every component itself has different potential for issues with reliability, especially if the PCB goes into a harsh environment. For example, like being mounted outdoors on some kind of communications pole, or underneath the hood of a car, or even worse, like out on the ocean somewhere, or going up into the atmosphere or into space. And so those types of environments are extremely challenging for electronic assemblies. And so there's a need for higher reliability alloys all the time, especially in the lead-free segment. So like with military and aerospace, medical devices, there are exemptions, and they can still use a lot of tin lead, which is known to be reliable and it lasts for the lifespan of the device. Well, there's a really slow change, though, happening in those industries, and eventually they're going to have to go lead-free. And so these higher reliability alloys, as well as low melting with additives, are becoming more commonly tested and used for those types of applications.
I think you brought up something just a moment ago, which was not just the solder itself, but it's also the bond that it forms to a pad, and then also to the actual the lead on the component. So is there any work there to try and improve the bond there to prevent fracture there? Or is the predominant challenge been fracture within the solder joint itself, where you still have a really strong bond to the pad and to the component, but the solder joint itself is really where the failure point is?
Yeah, what I see happening is the folks who are doing research on solder alloys and solder joint reliability are the solder manufacturers. And there's a little bit of that work being done by bigger OEMs like Intel, for example, or consortiums like INEMI. And they'll publish papers periodically on their testing. But those are, I mean, really the financial incentive to develop a new alloy that's going to dominate the market is in the hands of the solder manufacturers largely. And so we're constantly doing work and writing papers and researching new environmental test requirements. Like, for example, in the automotive world, they've expanded the testing range. Some companies that we deal with now want to test from negative 40 C to 175 C in thermal cycle testing. That's pretty aggressive. That's difficult for components and PCBs and solder joints to all expand and contract at the same rate in that environment. So there's going to be a failure in those types of environments. Whereas in other applications like household electronics, the temperature is pretty stable around your household computer, your television, those sorts of things. And so the requirements are not nearly as stringent. So it really depends on the end use application. And a lot of the research is going towards high volume applications like automotive.
I was going to say for household or for consumer devices, it probably seems like the main requirement is, mechanical shock. How often do you
Yeah.
drop your your iPhone or your smartwatch or whatever? But that's pretty surprising. I mean, that there's such a wide testing range that's being demanded now for automotive. I wouldn't have expected that in automotive. I would expect it in maybe like commercial space or aerospace or something like that. Um, but automotive negative 40C all the way up to, you said 170, I think. It's pretty.
175 I've seen recently. Yeah.
That's a pretty broad range.
Well, that's based on actual temperatures, of course. Like negative 40C could get hit somewhere if your car's outdoors, say in Alaska in the
Okay,
wintertime.
that's fair.
Yeah. And then it's going to get up to 175C on certain parts of the engine. So depending on where those modules are mounted. And as you know, we're putting more and more electronic modules into cars all the time. We want to add, safety equipment, all kinds of sensors, lots of electronic gadgetry inside of the cabin of the car, and all the sensors that feed into that and give you real time data. And then, honestly, I heard the folks uh, who are building electric vehicles. One particular company described electric vehicles like an iPhone on wheels. And so they look at it from the point of view, it's almost like a computer that is now designed to roll around on the road. And so there's way more electronics within electric vehicles than there are in common everyday cars.
Well, that's true. And actually, one description I had heard recently kind of goes beyond that in terms of what they look like in the future, which is data center on wheels. You
That's
actually
it.
have like you have server level, computing in some of these vehicles in order to support all of the autonomous systems and sensor systems, and I mean all the data flying around between all of it. It's just a ton of stuff that they're going to have to pack into these vehicles.
Yeah, it seems like they're becoming more and more software driven as well. I know that's kind of been Tesla's approach, where they built the car mechanically. It's very simple mechanically comparative to gasoline powered engines, where there's very few moving parts, but there's a lot of electronics to control everything. And of course, Tesla wants to just send you updates over the air while you're not even using the car. I understand that updates occur almost nightly sometimes, and they're fixing things through software patches rather than through hardware repairs.
Yeah, that's a great point. I actually my car that I have is 5 years old. I think I've seen an update once. It's not a Tesla, but I've seen an update I think once in that whole time, and they're doing everything what nightly. That's a lot of updates, and that's a
Well, I
lot of
think
data flying around the car.
I assume also Tesla's gathering data. I don't have a Tesla, but I've heard that they're looking at how you use the vehicle and they want to track that.
That makes sense. So they have to have a lot of stuff all over the place in the car, including in locations that could be very hot.
Yes.
Yeah. So the other thing about plating, you mentioned that the solder companies have, of course, an economic incentive to develop the most reliable, solder pastes that they can develop. But what about platings? Do they work closely with the plating developers, whoever might be doing that, or are solder companies working on plating?
Unfortunately, those are very separate industries. So the bare board manufacturing world is very separate from the PCB assembly companies, and they're also very separate from component manufacturers. So in many cases, they kind of take what they get. They're given PCBs, given components, and they just have to try to solder them together and make it work. And they don't have control over the plated finishes that are on those materials. In some cases, they do. But there are certain standards that are used. I mean, there's a selection of about 5 or 6 common surface finishes on printed circuit boards, and maybe 2 to 3 metallic finishes that are used in components that are fairly common. And generally speaking, most assemblers know how to work with those finishes. But it's when they get something out of the ordinary, or like in the last few years, there have been pretty horrible component shortages or supply chain issues. And so I hear problems with customers switching components from time to time, and they'll take something that's similar but maybe with a different finish on it or a slightly different size. Like maybe they'll substitute an 0805 for a 1206 size capacitor or something, and just try to make it work on their assembly so they can get it built and shipped.
Well, what are the problems that can result from that? I mean, you can come up with, I think, cases in high-speed digital or RF that are maybe more advanced or maybe more specialized where you don't want to switch out for different case components. But it sounds like you're talking in terms of assembly more generally.
Yes. Yeah. Yeah. So, I mean, just in general, like I said, we deal with contract manufacturers usually, not OEMs, not, the end user of the devices. And so the contract manufacturer is just going to do whatever they need to get that board shipped.
I mean, that's understandable. I'm sure that they're trying to cycle through the prototypes as fast as they can, or maybe earn business at higher volume. Um, but are they aware of the possible defects that can result from the incorrect pairing of components with solder?
I think
How
so.
aware are they?
Well, most of our customers do some type of functional test. They're doing
Okay,
some type of electrical testing. Plus, some of them do burn in testing if they're requested to do that. Of course, there's added fees for some of that testing. And so it's really up to their customer who's paying them to do that.
sure, that makes sense. Well, I mean, what other tests might they need to do, or what other defects could they see from incorrect selection of solder?
Well, the biggest potential problem since the advent of the lead-free area would be accidentally using tin lead on a lead-free specified circuit board. Of course, that would be a huge issue, especially for contract manufacturers who have both tin lead and lead-free solder alloys in-house, and they're building both types of product. So it's not a common mistake, thankfully, but it could happen that they might inadvertently switch alloys. And then the tin lead alloy, as we know, lead is being banned because of health and environmental concerns with it. And so that would cause the scrapping of an entire job that they built if they use the wrong alloy.
Yeah, I can see the reliability or the liability issue that arises with that. What other kinds of defects do people run into with incorrect solder selection? I mean, are there warpage related defects? The other thing I wanted to ask you about when we have a moment is tombstoning.
Oh, yeah, certainly. Yeah, tombstoning is one of the common defects that's been around for a long time. So that's a problem with alloy combined with reflow profile, combined with design of this PCB, where you have thermal differences from one pad to another. And then if depending on exactly how you're assembling that board, or if you substitute components, like in the previous example, I was talking about substituting maybe a different size capacitor or resistor for a larger or smaller version. It's not going to fit the pad set on the board exactly. And if it doesn't fit the pad set and it's shifted a little bit, or if it's in between the pads, that creates higher potential for things like tombstoning, skewing, shifting. So that's one potential common problem. I mean, if you pick the wrong solder alloy and let's say you have two different lead-free alloys, one of them might be Sac 305, which is standard. One might be a low silver version of that alloy. The melting points can be a little different. And so when you reflow those, it's possible that you might not reflow it with the correct profile. Also, when you go to rework those solder joints, or if you're doing inspection of the solder joints, they'll look a little different. And so the inspectors might find false calls, or the AOI might find false calls on errors of a different looking alloy when it's expecting to see Sac 305 and it sees something that's not Sac 305. So really, it's not so much of a real quality problem if you're substituting one lead free for another, because they're all pretty much tin based alloys. But it might result in like extra work on the part of the assembler and extra time and labor.
One thing I've wondered about tombstoning is how common or how prevalent it really is. Because if you, I bring this up because if you look around the internet at DFM guides or DFA guides, um, they always bring up tombstoning, and I think the fact that that happens in all of these different guides that you see online, it implies that it might be a more common problem than it actually is. I mean, I've done my share of boards, and I only had it happen just barely one time, and it was easily fixable by just plopping a little bit of solder on there, and it was fixed, and it was only on one board. So I guess I just wonder how common is it really?
I think when our customers see it, they usually see it on an entire job, and then they spend a lot of time doing
Okay.
touch up to rework those components. But it is easy to rework. You can remelt the solder joints and shift that component and place it, and it's fine. The other defects that are more difficult to rework would be something like any kind of head and pillow on a BGA. So if you got one sphere in the center of a large BGA somewhere that's not soldered properly and it's getting intermittent connection, that's a real issue, because you pretty much have to melt all the solder joints, remove the BGA, put down extra solder paste or gel flux, resolder it, and hope it doesn't happen again. And then voiding in solder joints are another huge issue that I hear customers complain about, because it's hard to rework voiding. It's hard to get rid of voiding. Once you have it, it tends to form again in the same solder joint.
So with head and pillow, you mentioned this is on BGAs. I'm going to assume that this is something that would have to be visually identified from X-ray inspection, or it's being tested live and you get that intermittent failure, or you get no connection at all.
Mm-hmm. That's correct.
Okay.
Yeah, and
then what?
it's going to happen only if you're doing full inspection of every BGA, of course. So if you're building pretty complicated boards and you have 5 to 10 BGAs on a PCB, and if you're building a 1,000-piece run, probably not going to do 100% X-ray inspection of all of those, because it takes a long time to do that.
That's fair. That's fair. Yeah. And then with voiding, what's the inspection process for voiding?
It's simply X-ray measurement. Usually it's 2D X-ray, and some systems don't have the ability to measure actual void area. Others do. And usually I hear this complaint a lot, actually, that our customers are being given pretty low void limits by their end user, and they're trying to hit that. And if they can't hit that, then they'll do everything they possibly can, switching solder alloys, switching solder paste, changing reflow profiles, stencil design changes, up into including rework in an attempt to try to get rid of the voiding. But like I said, once it's occurring at a high rate, it's difficult to get rid of it in some cases.
Well, what's causing it?
There's a combination of things. I mean, the PCB surface finish plays a role. The PCB design, I think, has a huge role. Usually it occurs on bottom terminated components like QFNs or LGAs. And usually it's pads with via holes plated in them, which is commonly done to help get heat to transfer out of the component. And they are just great they're great environments to create voiding in that situation. When you have vias in the pad, sometimes vias can help reduce voiding. Sometimes it helps voiding to increase. And it's the component themselves, the metallization on the component. The solder paste flux is a huge contributor to it. Usually that's the first place customers want to go. They want to blame the solder paste supplier. So I get to have lots of phone calls about that when it's occurring. But, every solder paste company over the last, say, 5 to 7 years has released multiple versions of ultra low voiding solder paste to help really specifically address that issue. So looking at it from a solder paste point of view, what can we do to minimize the voiding as much as possible? But if a customer is using an ultra low voiding solder paste and they're still seeing high voiding levels, then we have to start looking at the PCB design and the metallization, the stencil design of the solder paste print, the reflow profile. That's where I get involved pretty heavily and talk through that with customers.
So like on a bottom terminated component, that pad where it has, a small array of vias in it, it sounds like one of the things that might be happening, and correct me if I'm wrong, is that when people create the component or they just find the component online, the paste mask or the paste stencil just has an opening that just matches that pad. And they're not thinking about, number one, is solder going to wick through to the back side? But number two, is there going to be too much solder resulting in voiding? Or is there going to be enough room to vent any material that might start evaporating out of the paste? Are those issues that can all contribute to voiding?
Certainly. Yeah, the stencil design can have a huge effect. And companies who are skilled at manufacturing stencils, and there are many good ones. We have a partner company called Blue Ring Stencil that manufactures stencils. They have their own engineering guidelines. So if a customer sends a stencil layer to them, a solder paste layer, they'll look at it and they'll apply their own design rules to help mitigate any kind of problems with voiding or tombstoning and other types of issues with BGAs as well. And they'll make the stencil design, they'll optimize it in some sense with their own design rules.
Well, I'm wondering what that optimization is, because I think it's important for designers to get that feedback at some point as far as what should the paste mask opening look like. instead of just kind of hoping that whoever they send the data off to is going to apply this optimization.
That is a problem in the industry, to be honest, because as you know, in component specifications, there's a recommended solder paste print usually. Sometimes there's not. It depends on the component. And then the customers have different level. Our customers have different levels of expertise of stencil design, and so they will sometimes make their own edits and they'll optimize the stencil design to help solve problems that they've run into in the past and that they're knowledgeable about. And then sometimes customers just send the data over as is as a paste layer. And like you said, there might be a one-to-one aperture opening to the pad on a big thermal pad. And if you actually printed one-to-one on, say, a QFN thermal pad, way too much solder paste. That component's going to float. It's going to rotate during reflow, and it's not going to work well. And so stencil designers generally know that because they have had a lot of experience building stencils over the years, and they're going to look at that and catch it, flag it, hopefully, and make a correction to it without being asked to do so. But in some cases, customers, I mean, we do have very knowledgeable customers as well that take great pains to design their own stencils based on their knowledge of building product over time. I don't know how that information could get fed back to the designers, but I wish there was a good channel for that.
Yeah, one of the ways I think you can get that information back is, of course, to just send a report over to the designer. You know, assemblers can do that, and I've gotten those reports too when I send in something and they say, "Hey, you should probably have teardrops here. We'll add them. This is just FYI." It's a really simple way to just give that information back to the designers. So that way, when they come back to you, or hopefully they come back to you as an assembler, with more assembly orders, they cut down that NRE time required to get the board into assembly.
Yeah, that sounds like a great idea.
Well, hopefully it happens more often. So with these large thermal pads too, I'm wondering, is a decent strategy for a designer to just apply a negative paste mass expansion?
You mean like pull it back in?
Yeah, exactly. Just pull that opening in a little bit by, I don't know, a couple of mils, or maybe to 75% of the area, something like this. Is there a rule of thumb?
Yeah, the rule of thumb that is normally applied on thermal pads like that is to cut it down at somewhere between 60 and 80% of the total area covered with solder paste, and then break that deposit up with some window pane type openings going through it. So imagine a crosshatch going through the solder paste print, and that allows gases to escape during reflow to make sure that the gases aren't contributing to voiding on the thermal pad solder joint.
Yeah, I'm sure some of those gases can accumulate also as residues as well. Is that also a problem?
Yes, yeah, and if you reduce the amount of solder paste too much, like if you took it down to 50 or 40% area of coverage, then the solder paste might not be enough solder paste to flow and wet everything properly, and actually to drive the voiding out of the solder joint. And so you can have voids created from lack of flow.
Too much or too little gives you voiding.
Yes. Yes. And if there's vias in the pads that are open and they're plated to the bottom side of the board, if you print solder paste directly over the via, it's going to flow to the backside. And that's draining solder out of the solder joint, essentially. That can contribute to voiding. So it's best to print around those vias or mask them. I've seen a lot of designs recently where there's solder mask being put across the thermal pad to break it up and actually protecting the vias so solder can't flow down the via holes.
So is that like almost like a window pane style set of, solder mask lines that basically cover up those vias?
Yes. Yeah. Or the next step of that would be to take the thermal pad and break it up into some type of window pane so that it's not one big thermal pad.
That makes sense. Yeah. Or you could, I guess, plug and cap those vias.
Yeah, that is helpful as well.
Okay. Adds additional cost though. I think that adds up over, however many boards you have to run.
Yeah, certainly. Yeah, that's definitely an added set of processes that the PCB manufacturer has to go through.
Okay. So with this push towards higher reliability with lower temperature, is this something that's going to continue to proliferate in areas like EV or like aerospace or telecom, some of those areas that we mentioned earlier? Or is this going to become a new trend where just everybody else is going to start to get on the lower temperature solder bandwagon?
Where I see low temp solder being really promoted and pushed is for more consumer electronics like computers, televisions, those sorts of things, because they don't go through extreme thermal swings usually. That's the one problem with low temp solders. If you're using like eutectic tin bismuth, which melts at 138 to 140 C, depending on the additives, that's pretty low. And so you can't put those types of things inside of like under the hood of a vehicle, for example. And you probably wouldn't want to put them into any kind of aerospace environment. Now, but in household use items or in the interior of a car, even, it's probably fine. Now, they're not necessarily lower cost. A lot of them actually are a little higher in cost, but they're getting to the point where they're as reliable, equal to or better than SAC 305. And the real advantage that low temp solders give you is you can run a much lower reflow profile temperature. And so you can save energy from not running your oven so hot, because usually our customers will turn the oven on and it's on all day. So they're constantly heating and exhausting hot air, essentially. So if you can run that at a lower temperature, that's helpful. But the big benefit from it is reducing warpage related defects. So any kind of thin PCBs, large components like larger BGAs or LGAs or things like that, they all have different expansion and contraction rates, and the solder does as well. But there's constantly warpage going on, especially with BGAs, that creates head and pillow. And if you can reduce the reflow temperature, it minimizes the warpage, and so head and pillow becomes less of an issue. Like we were talking about earlier, head and pillow is difficult to rework because of the warpage potential of the component versus the PCB. They warp differently. And if you can reduce that temperature, you have a better shot at making a quality solder joint.
So, of the, or I guess out of the customers that you have talked with and consulted with, what percentage would you say have implemented or are planning to implement low temperature processes? Or do they even need to do any changeover? They just need to buy the solder paste and turn down the reflow temperature and they can run it.
They can pretty much just buy the solder paste and turn on the reflow temperature and run it. Every solder supplier that I'm familiar with has low temp solder pastes and also has higher reliability versions of those with additives to make the alloy stronger so they're not as brittle as traditional tin bismuths. But with that being said, the availability of like wire solder, low temp wire solder for touch-up and rework is pretty limited. Also, low temp bar solder is not readily available for most of the alloys because bismuth itself is the main additive to reduce the temperature, and it oxidizes very quickly, very readily, especially if you had an open wave solder pot that's open to the air. You're going to create a lot of dross, and then you're going to be adding a lot of that tin bismuth bar solder back to replenish for the dross that you're removing. And the cost of running that process would be very high compared to SAC 305. So what I'm seeing more is customers that are using low temp solders are buying them in solder paste form only, and they're touching up with SAC 305 wire, and they're through hole soldering with SAC 305 in their wave. And it's a mixed bag of alloys on that PCB then when you're all finished. In fact, that's true of BGA assembly as well. BGAs typically come with SAC 305 alloy, and it's expensive to have them reballed with some different alloy. And so most customers are making hybrid solder joints, low temp solder on the solder paste part of on the pad, and then SAC 305 BGA, and there's some mixing going on within that. So there's a lot of testing being done on the level of mixing, how much mixing do you need to make a reliable solder joint, and so on and so forth. So it's a big question. It's under a lot of scrutiny right now.
Well, with the hybrid assembly, or I guess the hybrid solder usage in a PCBA, is there a reliability issue that can arise there? Do you create a set of components that essentially become the points of failure in that board? Because if there's going to be a reliability issue, you would expect it to affect the entire assembly and then hit those points of failure, and then that's what creates the failure of the entire device.
Yes.
So I'm wondering if just one of those types of solder becomes that point of failure in that PCBA.
Yes, definitely. Yeah, hybrid solder joints, from what I've seen recently, are not as reliable as if you had one uniform alloy. So, for example, if you had just a SAC 305 solder joint on a BGA, that's going to last longer in reliability tests. Or if you had just low temp solder alloy for both the solder sphere on the BGA and the solder paste, that uniform mixture is more reliable than if you start mixing the tin bismuth low temp solders with Sac 305 and you have incomplete mixing typically, because the Sac 305 is not going to melt fully in a low temp reflow profile. And so that level of mixing really directly correlates to how long those solder joints will last, especially in drop shock type testing.
So what can be done to overcome that problem? Can there, I mean, is there anything that can be done with the processing itself?
Well, I think it depends on what the requirements are for the device and how long it has to last. If we're talking about consumer electronics, I mean, what's the lifespan of a cell phone? 1 year, maybe two,
Yeah.
or a PC even a couple of years maybe. So I don't think that the designers and the OEMs are really that concerned about the reliability of where they're applying these mixed metallurgy solder joints. But I don't think they're being used in mass production yet either, that I'm aware of.
That's a fair point. Okay. So I think the takeaway here for a designer is really to think about the lifetime that the device needs to perform at before you start specifying solder, and then probably work with your assembler to see what the best options are to hit those targets. Is that a fair point?
Yeah, definitely. I think it's always good to look first at what do you expect the device to do? Is it a class 1, 2, or 3 device? How long do you want it to last? Do you have warranty on the product that is 1 year or 15 years? Those kind of questions are real important when you're choosing the materials, especially the solder materials, because it seems like the solder materials are where your failures are going to occur. I wouldn't say by design, you'd know better than I would, but it's kind of like they're the expansion joint in the road, if you will, between the component and the PCB. When you have thermal cycling going on, something's going to give eventually, and usually it's the solder joint.
Well, I mean, in more advanced or more dense designs, for a long time it was microvias, right? The microvia reliability was such a big problem, and now it seems like we're right back to solder.
Well, maybe where there's a pendulum swing where now designs have switched.
Yeah. Maybe when we come up with the next interconnect style, vertical interconnect style, that will be the reliability problem again. So is there a delineation specifically for different class devices for class 2 versus class 3, essentially? And are companies marketing solder specifically for those classes? Or do designers really have to look specifically at the performance requirements, regardless of which class they're in, and use that to determine which solder they should be working with?
Yeah, we don't market products specifically for one class of device. Instead, it's more about the designer and the specification for what that device needs to do. And I've seen, I don't know, sometimes designers or the customers of our customers will send the design drawings over the files, and they are allowed to pick their PCB manufacturer and specify things like the finish, and then pick their solder and pick the components that they want to use, and they have a lot of autonomy. But they're going to build it to some, usually class 2 is a good middle of the road, unless it happens to be medical aerospace or something that has to never fail essentially. Or they'll get a very detailed set of designs and prints and requirements from their customer. And then they try to make it fit whatever those requirements are, and everything in between, really. But by default, they're going to try to follow the IPCJ standards as a rule of thumb, if nothing else is given as guidance.
I think that makes sense. I think that makes sense. That we have industry standards for a reason, and they're certainly helpful for normalizing whatever those performance standards need to be. So I think that makes sense for them to follow those standards. So what's next for lead-free solder? Are we going to see much greater infiltration of lead-free solder into mil aero, some of these other areas in the near future? I know that going green has come in vogue again, and I'm just waiting for the lead-free debate to crop up in the mil aero space and probably in the medical space more, because out of all of the stuff that happens with environmental friendliness and energy efficiency and things like this, all these environmental discussions, lead-free solder doesn't really seem to be on anybody's list.
I'd agree. Yeah, I don't think it's on any short-term list for mil aero applications. Although there are constantly NASA, DoD consortium projects going on where they're testing the reliability of various lead-free alloys, but they're nowhere close actually putting them into practice.
I do sometimes see those reports come out, and I've seen them in the past. And every time something like this comes up or someone starts discussing it, it just makes you wonder how close we really are.
Well, from our point of view, that's a pretty low volume on consumption of solder products. And so solder companies are driven to chase the bottom line, of course, like all other companies. And so we're going to market and sell alloys that are usable by the bulk, the high volume manufacturers. I mean, things like cell phones, like electric vehicles, or just the automotive industry in general. LED lighting is a huge volume consumer of solder products, all those types of industries. So we're going to market alloys and solder products for those applications more so than for the mil aero area.
Sure. Well, and not to be anti-environmentalist or anti, going green or anything like that, but I've just wondered if, the mil aerospace, because like you said, it is lower volume, going to lead free in that area is maybe a solution looking for a problem.
That's a good way to put it.
So you wouldn't disagree with that kind of statement?
I would agree. Yeah. And I think it'll eventually happen, but it's going to have to, they're going to have to do decades of testing before they'll settle on one alloy. And I think once those industries settle on an alloy, they might have one or two choices, and that's what they're going to go with. And it will most likely be something generic. It might be some modified SAC solder with antimony or bismuth or something to strengthen it. I don't know really. I mean, they're testing a whole wide array of different types of products with lots of different additives.
Interesting. I mean, it almost seems like kind of the possibilities are maybe not endless, but there are a lot of different possibilities for these different alloys that can be developed and tested. Because like we said earlier, you're essentially just mixing a bunch of metals together.
Yeah, we are. Yes. Yeah. But there's a lot of scrutiny over the microstructure and where all those elements go into the intermetallics and where do they segregate within the finished solder joint, especially when you do thermal cycle testing or something where things start migrating and changing over time. And so you get sometimes agglomeration of different particles and the solder joints lose strength over time. That is one historic problem.
That's another thing that I think I should have asked about earlier is stability. How does the stability of all these different solder alloys compare? Like a bismuth, or solder alloy that contains bismuth versus like tin lead?
Well, they're all different because it really depends on the other metals that are present, like we spoke about earlier. So the PCB surface finish can play a role, as well as the copper on the PCB pad. Certain finishes let the solder actually bond directly to the copper. Copper slowly migrates into tin over time, and then you get an accumulation of the Cu6SN5 intermetallic, so it's a mixture of copper and tin, that can form kind of brittle layers. And then that's wherever the weakest point is going through the solder joint, that's where they're going to fail eventually.
Yeah, so you get crack propagation and then eventually complete fracture.
I mean, that is the thing is there is no solder alloy that I'm aware of that is 100% stable. So like an as soldered condition, if you look at an SEM photo and an elemental breakdown of where all the elements are, they never stay put. After time, those things move around and change and form new intermetallics.
Sure, that's understandable. Well, this has been very interesting. We're getting up there on time. But Tony, I want to thank you so much for coming here and talking to us. I always like to talk to folks from the manufacturing space, and this has been very interesting to exercise the chemistry side of my brain again, because I don't get to do it enough.
Excellent. Well, thank you for having me. I really appreciate it.
Absolutely. To everyone that's been listening, we've been talking to Tony Lentz, chemist and field applications engineer at FCT Solder. If you're watching on YouTube, make sure to subscribe and hit the like button, and of course, leave a comment or question. And if you subscribe, you'll be able to keep up with all of our podcast episodes and tutorials as they come out. Last but not least, don't stop learning, stay on track, and we'll see you next time.